All right. Hello, everyone. Thank you for listening into our video about our MSD project. I hope you enjoy learning about some sailing and our project. The project team is me, Sullivan Shackford. I'm an industrial engineer. We also have Christian Gallo, who is our mechanical engineer, Emily Arison, our electrical engineer, Tori DeCesar, our other electrical engineer, and Umar Dillon, our computer engineer. So what is an Ollie Box? In a sailing regatta, each race is started by the sounding of a sequence of a signal that allude to the time left in the starting sequence. So most of the races that we do at the RIT Sailing Team is 3-minute starts. So usually these signals are whistled by a race officer using just a standard safety whistle or sport whistle like a referee would use. And usually this is not very loud, but an Ollie box takes the place of the race officer as the automatic horn system to sound the signals so that the race officer can be more focused on the safety and the start and the legality of the start too, to see if there are any fouls or anything, and they don't have to deal with the timing and blowing the whistle. So the project problem, RIT Sailing Team has a lot of members now. It's been growing very quickly in the past few years. And the practices tend to have a lot of kids and a lot of boats. And racing is always a part of our practice. And we also host regattas that require race officers. So having an Ollie box will reduce the need for a race officer and or a team member running the practice to focus on the timing, focus more on coaching and watching out for safety purposes, because it is difficult for a student-run organization to be having these races or even just the practices, and they're running and paying attention to the timing, and without the need to pay attention to the timing, it's a lot more safe for them to be running the practices.
The client's expectation of the team was to create a functional Ollie box that has the ability to sequence a dinghy race, 3-minute start. It also should be able to lash down to the boat secure. It shall be waterproof. It shall be lightweight and easy to carry.
This is our approach that we decided to take, where the communication between distances would be performed through the use of the ESP32 module and an Arduino, while the communication to the user would be through a TWIDAC horn system and an LCD selection screen. Wiring for these primary components as well as additional components can be seen over in this schematic, where there's two different types of circuits. There's the topmost circuit, which refers to the system that would be implemented on different individual racing boats, and the bottommost circuit, which would be implemented on committee boats.
This was our approach to test the horn. It was very important for us that the horn is not only able to be heard by all the races, but is also safe for the users to be using. So we tested the horn at varying distances using an OSHA-approved decibel app, and this is some of our findings that we had. We found that the maximum output of 135 decibels at the horn and about 85 decibels about 200 feet, which met all requirements.
So for the mechanical design of the system, the whole sequence system was contained within this waterproof box. The horn, compressor, screen, and buttons were all attached to the top of the box. And inside the box, the battery and UWB boards were held in place using custom 3D printed brackets, Velcro, and screws. And then all components were waterproofed using silicone or acrylic spray. So this video shows our approach to tracking the boats. Distance 1 is measured between the UWB tracker on the boat to the top pin, and distance 2 is to the bottom pin, and then distance 3 is to the additional tracker on the committee boat. Then using these distances in the law of cosines, we can find the horizontal distance to the finish line and then determine when the boat has crossed the finish line. The third tracker is used to make sure we know which side of the finish line that the boat is on.
On the physical selection screen, the user would be allowed to select from different types of horn sequences, including 3 minutes, 5 minutes, 10 minutes. And the number of times the horn would sound would be dependent on that selection. The LCD screen would additionally display an appropriate countdown in regards to how long there is until the sequence actually starts in correspondence to the different selection. So a 3-minute selection would lead to a 3-minute timer, 5-minute selection, 5-minute timer.
So we completed 95% of the testing. The only testing to remain is testing on the water. Unfortunately, there were no races going on when we got to that point of the project. So that will be tested in the spring.
The only real challenge we faced during this project and had to overcome was the detecting the finish order and over early penalties. The main problem with that is the requirement to track the boats in order to perform this. And the only issue was the cheapest method that we were able to find was very limited stock. Therefore, we cannot get enough to track the entire sailing regatta, but we did have enough to track one boat. So we were sort of able to at least do a proof of concept in order to track a boat accurately and use these data to find the finish order. If we had more time or limited stock, we would be able to complete this. That was what we were able to prove.
As our final acknowledgements, we would like to thank our clients, the former RIT Sailing Commodore Ethan Hall, the Sailing Team Advisor Dr. Kate Leopold. We also like to thank the sailing team for their continued support. Thank you.